3, Black Hole and Orbits. So the purpose of this lab for part 1 was to find the mass of the black hole, and this was done by using motion data to determine the mass of the black hole by analyzing the star's orbit and applying Newton's laws of motion and gravity. And then part 2, Orbit Without Crashing, the purpose was to simulate the gravitational interactions between a planet, its moon, and a spaceship to determine the initial velocity needed for the spaceship to achieve a stable figure-8 orbit influenced by both the planet and the moon. And so some key concepts. First, we have Newton's law of universal gravitation, and this is the law that defines the force of gravity between two objects in space as a product of the two objects' masses and a gravity constant, divided by the distance between the two objects squared. Note that the force that one object exerts on the other has an equal and opposite force due to Newton's third law. And then some other relevant concepts are the momentum principle, which describes the net force on an object being equal to the change of momentum over a change in time. And then we have the update formulas. The velocity update formula allows you to update an object's final velocity based on an initial velocity, a net force, the mass, and a time interval. And then the position update formula allows you to update an object's position based on its initial position, its average velocity, and a time interval. And then also forces in the parallel and perpendicular direction. So a force in the perpendicular direction will change the direction of the momentum, while a force in the parallel direction changes the magnitude of the momentum. And then this is my code for part 1. The system was the star, and then the surroundings were the black hole. So I had initial conditions, as you can see in the top left, and then I had to edit the calculation loop and had to insert my email in order to get a specific mass for my lab. And then here we used the momentum principle in order to find the mass, and we were able to calculate Fnet through calculating Fnet parallel and Fnet perpendicular individually. So the mass of the black hole in my simulation was found to be about 1.39 to times 10 to the 34 kilograms. And then in part 2, our system was our spaceship, and then the surroundings were our planet and our moon. And in this case, we had to use trial and error to calculate a valid velocity that would allow the spaceship to orbit the planet and the moon without intersecting or crashing into either orbits. So what you had to do was find Fnet on the moon and Fnet on the spaceship using the coding and GlowScript. And as you can see, the initial velocity that I found through trial and error and by calculating forces was negative 4.3 times 10 to the 4th, 4 times 10 to the 5th, and then 0 in the z direction. And the spaceship's trajectory became very close to the orbit of the moon, but it never fully aligned with it or intersected it with the initial velocity I found using the model. Additionally, I was unable to find a stable figure-8 shape through the trial and error process. And some sources of potential error are round-off errors through calculations, and this is because the loss of precision that occurs when you round off a calculation would have like a snowball effect as the lab goes on, just increasing the amount of error. And then another possible source of error is this assumed physical omissions, such as there not being any non-gravitational forces on the planet, the moon, or the spaceship. And then 3, we assumed that all masses were point masses and had a fixed center, which definitely would have caused error because that's not accurate to real life or the simulation. And then 4, the use of trial and error to find an initial velocity for the spaceship in part 2 most likely caused error due to the wide range of potential initial velocities you could have used. And some takeaways and assumptions. One thing to take away is that the mass of the black hole was found to be 1.39 times 10 to the 34 through the simulation on GlowScript. And then some assumptions that were made throughout this lab is that gravity is the only force acting on the objects. The objects are point masses. The black hole and the planet don't move. The time step between data points is constant. And then Newton's law of gravitation and Newton's second law are valid throughout. And that the system is isolated. So there are no other masses exerting the gravity force on the system. And then so what does it mean? How does the net force and its parallel and perpendicular components differ from the change of momentum and its parallel and perpendicular components? So according to Newton's second law, Fnet is equal to the change of momentum over a change in time, and the parallel component of both vectors changes the magnitude of the object's momentum, while the perpendicular component changes only its direction. In practice, they may vary slightly due to approximations and how velocity and acceleration are calculated, and we can use dp over dt in place of fnet for this lab since we can solve for mass using dp over dt, while fnet requires the mass to be already known. And then if you want to predict the motion of the entire system, what will you need to include in your computational model? So all bodies were dynamic masses, and the model will need to include all the gravitational forces between the planet, moon, and spaceship, along with each object's mass, position, and velocity, so they can all respond to one another's motion. Using Newton's laws, their positions and velocity should update over time, and the planet's gravity would dominate in this model since it has the largest mass, and the force of gravity is directly proportional to mass. So that's my lab. Thanks for listening.